Hey friends, welcome back to another episode of Going Nuclear. I'm here with a really special guest. His name is Professor Hossam Gabbar at the Ontario Tech University. He's an esteemed professor who has a really unique background with mechatronics, electrical, and nuclear, and it's a really interesting mix. And we're going to be deep diving into him, his life story, and his career journey. So welcome, sir.
Thank you very much, and it's always a pleasure to meet you, and I think it will be very exciting today to talk about different aspects of my journey.
Sir, I know you have a lot of international experience. You have a lot of esteemed research that you're doing. Tell us about some of your, famous, or tell us about some of your most popular research projects right now.
Yes, if we would like to go in a journey, maybe I start with my first project.
Sure.
And that could be, it's quite interesting because when I say first project means when I was in my PhD studies and I was at Okayama University in Japan. And I remember that the first one was about designing a safety system with teleoperation. And that required to design robotic system with 7 degrees of freedom with infrared camera. And the other side, the teleoperation system with operation interface and operation management, where we would like to discuss or discover what are the conditions of pipelines and that was for nuclear facility, uranium enrichment facility, and it's a nuclear facility in Japan. And that was actually the first project. At that time, I remember I worked with 2 students working with me. They are master students and 1 undergrad student as a capstone. It was very interesting to see how things come together. At the beginning, we got a problem that they would like to reduce the risk on radiation on human at that area, and we started with that. That was really very exciting at that time.
Phenomenal. And tell me a bit about your career journey so far, right?
Actually, it is very interesting because we learn a lot through changes. I would say if a person, like in Japan, for instance, that it's typical that everyone join one job as a life job. They don't change regularly. Most of the professors or industrial, professionals in industry, they join one job and they stay forever till they finish. And that was quite interesting. So when I started in Japan, that was not my starting point, by the way, because originally I graduated from Egypt, Alexandria, where Alexandria University. It's very interesting that maybe I can give a little bit hints about that. Alexandria University, our engineering degree is 5 years, not 4 years. Here in Canada, maybe 4, in Japan 4, but in my university was 5 years. And my department, with one of 13 or 14 departments within the engineering, one of them is nuclear engineering. By the way, we are the only nuclear engineering in the Middle East at that time. There is no nuclear engineering other than that one in Alexandria University. And my department was automatic control. And automatic control, we study very heavily electronics for 5 years. We study control, modern control, digital control, embedded control, linear control, nonlinear, every aspects of control in around 5 years. And we study math. Our math is very strong. For 5 years, every year we take something around the math. And we study programming. So it was a very unique department actually. And in terms of in Alexandria University, we enter the university. We first enter something called like a common year. And after common year, you select which department you like to go. At that time, I really didn't know because there are so many things. So I said, okay. At that time, I was like the top 3 students in the department, in the whole university in engineering. So the way they actually mark is that, or you select your department, is that you make options. Option 1, 2, 3, and based on your grade, it goes to the computer, and the computer automatically say, based on your grade and the requirements, they say, I need 50 students here, 100 students here, and so on. So that department, automatic control, is the top 25 students or 30 students every year. That's it. Other departments like electrical, mechanical, production, manufacturing, civil, architecture, nuclear, marine, we have different departments. They select more, but our department was the top 30 students in the engineering. So at that time I said, okay, because I really don't know much, let me go the top. So I went into that automatic control. It's called actually computer and automatic control. That's the degree name. At that time it was very interesting, and at the beginning we start writing code. I didn't write code before in my life. Our computer was, I remember PDP-11 is like big, large computer, and no hard disk. It's just you write your code in a punching card. You put it in the punching card, and it just come after 2 days to get the run. It was interesting. Yeah,
That's phenomenal. So, so you got your foundations in electrical and automatic control systems. And tell me about what's next. Did you do your master's in Alexandria as well, or?
Yeah, that was quite interesting because in Alexandria we have a system where we have to finish 5 graduate courses, which I finished. But during that time, I decided to go to abroad, where so I finished my my graduate courses, and that's we call them master courses. And then I decided to go. I think at that time I went into research center, National Research Center. And after that, I decided to go abroad. So I went to Kuwait. I worked in automation for oil and gas for some time. And then I went to Abu Dhabi. I worked also in automation for oil and gas, safety, control, automation. And from there, I decided I need my PhD. But that is after few years where I got very good experience in automation, R&D, system design, systems engineering, all aspects of automation in process industry. We call it process industry. That's where I said I need to get my PhD. But it was good because at that time I got a good experience on what is the problem and what could be the solution, but with many cases. And that's where I started contacting some labs in Japan specialized in safety, process safety. And that was one of the unique labs in Japan, and I would say in the world, specialized in process safety and applied into energy. So we study energy and the process safety together. And that's where I started the first project for nuclear facility, actually, automation for safety and for diagnosis and control. And the second project was about also safety integrated system. And then I went to Tokyo University. After I finished my PhD, I went to Tokyo Institute of Technology. I worked as a postdoc with Japan Chemical Innovation Institute, where we developed a lot of solutions for biomass biofuel, again, process systems. We analyzed the biomass biofuel, plastic recycling across all Japan. It was very interesting projects. That's where I came to do, I would say, national level projects. It was a large scale across all Japan. It was 2 largest projects across Japan, biomass biofuel and the plastic recycling across Japan.
Before going into your master's program, you got a lot of experience in the industry, right?
Yes.
For your students, how relevant do you think that is to get a little bit of experience before jumping into master's or PhD?
A PhD. That's very interesting. About the experience, actually in our 3rd year, I worked as intern in Schlumberger. Schlumberger is one of the largest oil and gas exploration in the world. And they have schools to teach students in the before graduation as an intern. So they go every university and they select the top 5 based on 3 or 4 exams: math, physics, interview, writing, physical, like many exams. And then they select the top 5. I was among the top 5, and I went in school, summer school, to learn how to do exploration. And it's quite interesting because exploration, I have to know things about the oil and the gas process. I have to know about the tool. I have to know about the radiation, because some of the exploration based on radiation. So we have the badges and crystal, and we do this analysis. So we have to connect the tools, we have to monitor data, we have to analyze, we have to correlate to different profiles for oil and gas, whether it's oil, rocks, and we get some properties. It was very interesting because we, as a student at the time, I have all students across Egypt in one school. We spend 2 months or something, and after that we have to pass the test. And after passing the test, they give us a certificate that we are allowed to work actually as exploration. So that was quite interesting for students, especially new generation. You really have to seek large opportunities, and that is where you have to be prepared that you will be in competition. And competition means you have to be the top 5 out of almost like 5,000 or 4,000, because it's many universities. It's not one. All universities across Egypt, each university needs 5 students. From our university, I remember it was like 2,000 students or 1,500 students applied, and they need the top 5. So it is one good message for students that you need to work hard and you need to know that you have to compete. And that's from your day one into the university. I always encourage and inspire students in my classes that you need to compete. So every minute, and I always tell them that you spend 1 hour more, that's equal one degree in the final exam. That's equal to $100,000 in the first year.
Wow, man.
So, and that is really very important.
100%. Yeah, there's definitely a lot of opportunity that's there.
Absolutely.
So that's great. That's phenomenal, learning about your intern experience and getting that flavor of nuclear with the sources.
Yeah.
So tell me about your experiences in Japan. Like, how was that
Yes,
after
that was,
after contributing to the national projects?
Yes, so that was very interesting because we developed the patent, we made a venture company, and that was very interesting. And that's during my my postdoc time. After I got my PhD, I went to Tokyo Institute of Technology, working with Japan Chemical Innovation Institute, where we developed very nice patents and technologies, where it was very good because we developed a real product. And I remember we went to Yokogawa. At that time, we developed very nice technology for them for control automation, and that was a very good step for me to start thinking, what's my next? And that's as a postdoc, stayed for 3 years a postdoc, which is good, by the way. This is one of the also encouragement for students who would like to finish PhD. Sometimes they finish PhD and they would like to, I want to go to a job. If you would like to go to a career, you need to work in a large-scale research team. Because when you work in a large-scale research team, you will learn a lot of things from different people. And that's where you'll get a chance to get diverse views, diverse experience, and diverse also like problems. And from different views, mechanical, electrical, control, automation, energy systems, and nuclear. So that it was very nice to work in that large-scale team. Then I went into the situation where I got chances to go to international from Japan, or I stay longer in Japan. I decided to stay longer in Japan, and I actually got a faculty position as associate professor. And that's where I went to Okayama University as associate professor. Interesting, the department is called, or the division is called Industrial Innovation Sciences Division. That's as a graduate program, where I work in the systems engineering, but again, it's mixture between energy, automation, and systems. I remember at that time, my first project was smart grid. At that time, it was about, I proposed in something called Research Park. I developed and proposed for them very nice system to model energy mix with biomass, biofuel, hydrogen, renewable, and the nuclear. And I presented that in something called Research Park. And then I start leading national and international projects in the smart grid, including nuclear power as one element. So that was one really very good step as associate professor in my first career in Japan.
Phenomenal. No, it's phenomenal. And I know smart grid is revolutionary technology, right? And you're definitely an expert in that. Tell me about the value of smart grid with our energy demands increasing, and a lot of countries have to eventually replace their grids, which is very expensive.
Yes.
So tell me a little bit about that.
That is very interesting and very important, because at that time I remember when I went, Japan structure for energy and utility infrastructure is different than Canada. In Japan is similar to hierarchically one company. For example, in Canada here, you will have utility company who supply energy to your house. And this utility company or distribution company, they have to talk to another company in the same region, which is Toronto Hydro, for example, or Hydro One, then different names. So the distribution company have to talk to another company in transmission company. In Japan, it is one company all the way. So one province is just one company, distribution, transmission, and they own everything here. They do it hierarchically. It has advantage, disadvantage, but one of the main advantages is that if they want to do something, they do it. They don't need to talk to another company to take permission, and so the layers and barriers and conflicts are less.
So more resources to dedicate to projects.
And to do the job.
Immediately.
They don't need a permission from another company to do something in your region.
Interesting.
They can do it. So I started talking to them about microgrid. I remember I started microgrid, and I claim I'm the first to really talk about smart grid. In publication, I started talk about that since 2003. So I talked to them. I said, what about we develop something like small, like a microgrid, where we have the renewables and your electricity? Then we start talking. They start asking the question at that time, 2004, 5. They said, who will own the microgrid? We are utility. So if I install a microgrid in your house, if I have to maintain it, then I need the resources to really maintain every microgrid in every region, which is not doable now. And if I give you the resources to maintain it, it might impact negatively my grid. So it was some of the discussions at that time, which I realized that when I came to Canada 2008, we started talking the same problems. And it was very nice because now I prepared the way and prepared the methods and the models and the approaches and best practices to really implement microgrid in an effective way. So that was very interesting in Japan, and I took this further. Now, in terms of energy mix, like Japan have nuclear. That's before Fukushima. I was there before Fukushima, so Fukushima started like 2011, but before that. So the mix they needed. In Japan, they have two major resources. The hydro, they have a lot of rivers. So the hydro is one, and the second is biomass. Why? Because they have houses, they have earthquakes, houses, they replace the houses, they chip it small, and they get the biomass.
Oh, interesting.
So they have a lot of biomass. So now they start thinking, how can we mix them? And that's where we started talking. And it was very helpful. Also, Japan, they have relatively hot weather. So solar is promising. And also Japan is a set of islands. So we have a lot of offshore wind. And we have ocean, like wave, hydrokinetic. So we have different nature of energy system that could be very suitable for them. So we had a lot of discussions in this area, and for marine, energy for marine as well. That was very interesting. And that's why I have a lot of interest in marine energy, offshore, waterfront.
Yeah, it's phenomenal that this country has so many resources at its disposal, and I think smart grid technologies, there's no one solution to climate change.
That's
right.
correct.
We need to utilize
Mix of them.
all the mixes together.
All resources.
Right.
Yes.
All resources. So tell me about your trajectory in your career to more of the nuclear scene. When did that happen? When did you get into the kind of the nuclear side of things?
First, I started nuclear, as I mentioned. My first project actually at Alexandria University was handling automation for inspection, safety, monitoring for nuclear facility. At that time, as you know, when we deal with safety, it starts from process engineering. So we have to understand the process design, which is uranium enrichment for nuclear facility, what are the risks, hazards. So at that moment, we start increasing the interest and knowledge, and we got a lot of interest about that. The second layer or stage in this journey is during when I was studying energy mix in nuclear renewable or energy mix in smart grid. At that time, I have to measure, analyze nuclear power, capacity, generation, location, integration with the grid, the load profile, generation profile, what are the policies, constraints, requirements. So I started analyzing this, and actually we made a very interesting simulation tool to help utility and the ministry to plan energy mix in certain areas, including the nuclear power. So at that time, I continued my discussions and analysis of the nuclear power as a mix with certain locations, analysis. So that was since 2004 all the way. And of course, when I came here, I continued the smart grid with expansion of different aspects of control and safety. But again, it is around how to make nuclear power safe and integrated, reliable, and then expanded that further with SMR. So as of now, I am really, I teach courses actually, like public courses. I just taught one public course for nuclear renewable hybrid energy system. I had one workshop in the International Youth Nuclear Engineering Conference in Japan. And I developed that public course, and also I still consider that as one module in my own graduate courses, where I have a graduate course in a microgrid. So I have one module related to nuclear renewable hybrid energy systems, and I have activities and students working heavily in nuclear renewable SMR evaluation. I developed two new techniques and two interesting techniques about SMR in the loop. Now, this is quite interesting because if we would like to analyze SMR if I want to analyze SMR in terms of load following, now it will be very difficult to analyze that, and without a real SMR. So all what we will do is that we will assume either stable, fixed, full power, or if I want to have a load following, I need a model to actually integrate that with some renewable in the lab level and in simulation level. So we found that there is no. So what we developed, and it was very interesting and very impactful actually, that we developed hardware in the loop as SMR in the loop. So we represented the SMR as a model. We represented in electronics. And we integrated with real-time simulation so that we have now very nice domain and environment where we are able to simulate different scenarios, load following, and I have solar, wind, and I have battery, I have ultracapacitor. So I'm able to simulate that as a microgrid with SMR in the loop so that I can say, how can I support waterfront, how can I support island, how can I support northern area, how can I support mining site. I can get the load and I can just fit it into my model and get the best possible combination.
Phenomenal! Wow! That's really interesting, and I think it's really valuable because these technologies, these SMRs, which can load follow, haven't really hit the market yet.
Yes.
Right.
Yes.
And I think making these models and doing these simulations is so important. Right. Tell me about, nowadays our nuclear power reactors are base load 100% full power all the time.
Yes.
Right. Tell me a little bit about the different SMR vendors and how they can utilize these models and feed that into their designs.
Very good point. I would like to say a couple of points here. The first one is about load following. When I started analyzing the load following, and I discussed with many.
So for those that don't know, what, if you don't mind explaining what load following is?
Load following, okay, first, when we talk about nuclear reactor, we have the actual reactor that generates thermal, and the thermal goes to turbine generator. Now, load following is that the load is the grid or the actual load. If I'm saying I need load following, means if my load is changing this way, I need the reactor to follow that load. So it's not full power all the time. I need the reactor to change the output power based on the load requirements. So the driver is the grid or the load, and the reactor will follow. That's called load following. The reverse, which is reactor lead, or now the grid cannot dictate what reactor will do. I will say this is the maximum I can generate. If it is full power, if it is the first month's 100% and next and so on. That is the generation profile that goes to the grid, and the grid will have to take that and will have to deal with that. When I started the analysis, I discussed with many partners and many discussion groups. Why you need load following? That's the first question. So I started.
That's a really good question.
Absolutely, because at the first place, if you are the supplier or the vendor or operator of the SMR, you need to maximize the power because every kilowatt you get $1. Now, if I tell you load following, you'll say, wait a minute, that means I'm not generating 100% all the time. That means you are reducing your profit. Somebody is getting the pain here because somebody is losing money. So how can we make it a profitable case? And that's what we started. We started analyzing why me as a supplier or as an operator of SMR, I don't need load following. So we started analyzing these scenarios with case studies. One of them is that if I'm just generating to you and you are the grid, you have to receive what I'm giving you. But if you don't have that load, you need a storage. You'll pay a lot of money if you don't need that load. You'll pay a lot of money to compensate or to get that load as such. Then, so that's one. That means somebody have to pay for the battery. So we have life cycle cost analysis and the techno-economic analysis. We have done a lot of studies here. The second piece of it is that how the impact, if I don't generate all the time, that means I'm not really 100% consuming my fuel, which is not linear. So we need to now quantify how the load following impacts the fuel consumption and the cost of the fuel, cost of replacement, and other factors related.
It's a lot of factors.
So that is now the second piece where I started working on. I don't have answer yet, although I have general answer that there are some direct impact between the load following and the fuel consumption, that's for sure, but we need to create that model, and that's where I recently started working on that, and I took that also to the nuclear waste, because the nuclear waste will be impacted because you are reducing the waste. So now that's where I started analyzing, and this is very interesting area where I found it is very helpful for the operators, for the vendors, for the waste treatment, and for the power. Very interesting area.
Yeah, definitely it is. It's actually very valuable as well, because I think when it comes to small towns, right?
Yeah.
Or they're looking at micro reactors being put on the grid,
Yeah.
and hey, sometimes maybe in the winter time for these northern communities, they need more electricity.
That's correct.
Right?
And
So,
that's why that is the balance. And it's quite interesting because I also, one of the things we have been working with nuclear renewable and SMR as well, there are 2 points I want to highlight. The first point where Canada is, we call it state member in IAEA, International Atomic Energy Agency, where we have many countries. They are member. So IAEA, they started looking into why we don't develop standards, best practices, documents, technical documents about how to integrate, what are the challenges, what are the gaps, and so on. So actually, they called member state countries to send one representative. And I was member of this team from Canada. I went with other member, I think in CNL, if I'm not mistaken. But mainly from the technical side, I was representing the team to develop technical standards about all things related to nuclear renewable integration. From US, we had 2 members, from Korea, from Slovenia, from like many countries, France, like many countries, we had group of people working together to develop a technical document about nuclear renewable hybrid energy system roadmap, implementation, gaps, technologies, limitations, how to implement, what you expect as performance, application to integrate from the thermal, from the electrical, from the biomass, from chemical products, from water desalination and application. So we have done a very detailed document. It is published in IAEA, and it's recently published, by the way, just a few months back. But we developed a barrier, some sort of document or compilation of views. That was 3 years back. So this document, it was actually a very good exercise that we stayed we discussed in a week or so in Vienna, in IAEA. But before and after, till now, we have been discussing and developing and revising and editing to get the document to be fully executable and now published recently in IAEA. So this is very important document for those who are, especially for students as well, who would like to know what does it mean, nuclear renewable, what are the gaps, how to implement, what you expect. So we study things like coupling, the nuclear coupling with thermal, with biomass, with electricity, with hydrogen. All layers we analyzed, we modeled, we showed how to do and what are the expected challenges and how to implement and what strategy to do, and so on.
Phenomenal. That I think that's a really important undertaking and kind of
Very important.
cutting edge research,
Yes.
right?
Yes.
Tell me about some of the reactor technologies out there that are compatible with smart grid or with renewables,
Yeah.
right? You know, there's PWRs, which are like, hey, 100% all the time, right?
Yeah.
Or can-dos.
Yes.
But tell me about, you know, whether it's molten salt, whether it is the pebble bed designs. Tell me about your perspectives on some of the designs.
As part of the IAEA, we are required to list all SMRs in different countries, the stage of development, whether it is conceptual design, detailed design, it a research test, like research reactor, if it is under licensed or not, and when it is expected to be live, and so on. So we analyze all of those in different things, like moderator type, fuel type, enriched, not enriched, how much enrichment percentage, cooler type, the design, and then I further analyzed that with one of my master students. We went through like all types of reactors in terms of like the size, because sometimes the size and it can be related to the application. So we started correlating parameters related to the reactor versus the application. One of the things, of course, is safety. Safety is very crucial. I remember we had discussions with BWR where, like, you have sometimes when we discuss how many shutdown systems do you have? We say one. Okay, is it safe? Because we, as terminology, when we talk about can do, we need 2 shutdown systems. Then you say, but 1 is enough, and 1 can do the job. So this type of discussions about the reactor, BWR, molten salt, FR, like many, we studied a list of them. In terms of like which one is the best, I will not be able to comment on that for a number of reasons. First is because we do have collaborators from different reactors. For example, from Japan, we have the company started means they have a very intensive plan from Hitachi, Toshiba, and they are really looking into what is the typical size of SMR and what is the typical fueling cycle, like how long you need, because it's also huge, like, and also whether you are changing the fuel during operation or during shutdown, or whether the fuel is like the nature of fuel, the nature of moderator, like many aspects. It is not really a straight answer, but I would say that we have been analyzing number of factors related to number of installations. It is a very good exercise for students who would like to participate in the real deployment of SMR. This area is very interesting because a lot of parameters, and some of them are not well taken yet. Some of them, especially about the life cycle cost. I was talking to some team members from Korea, and we were talking about life cycle cost. Sometimes the life cycle cost is not well established. They miss something. For example, licensing. For example, testing. For example, research. If you have supercritical water reactor versus if you have BWR, or if you have the light water reactor, or if you have the fast breeder reactor, and so you would like to see differences in the regulation, in the licensing, in the testing, in certification. Now, when they are calculating life cycle cost, they didn't really went in that details. So they get just a power, fuel, installation, and really I felt somehow, and that's what was the discussion with the research team from Korea. We reached the point where we couldn't levelize cost, like sort of like costs that represent everything, not accurate enough. And I see this is very, very interesting and important point to quantify the reactor and map it to a certain application. I have a project and collaboration with Norway where we are now evaluating 3 or 4 reactors to be installed in a ship. And at this stage, we are looking even in safety, training. Like if you have a reactor that requires 100 hours training, another reactor that you need 200 hours training. Now, 100 hours, like when I say 100 hours per year, for example, for every person, for every monitoring, regulation. So it's quite huge. So that even the amount of training can impact the life cycle cost. And that was not well taken. And that's where I'm working with my students and with our collaborators, with Norway, for example, how to quantify that from safety, from regulation, from selection of even the position of the reactor. Even sometimes we were talking about the ship will go to a certain territory where the territory does not allow nuclear reactor on board. What can we do? So we need a separated propulsion system. For example, this is the reactor, you can leave it outside and the ship goes inside. This type of thing we have been discussing in detail.
Really cool how all of these factors go into just operations of a ship or a whole grid and a whole system, right? Yes. So, with our future here in Canada, and we've got a lot, our grid is going to change a lot, right? Yeah. We're projecting our grid to, double in size within a couple of years, right? Or within a decade, right? Tell me about integration of these principles within Canada's future, policy for energy and also investment strategy.
Yeah. That is actually very important, and I would like to give a background. We have been developing a simulator, and that simulator, I mentioned, it has two levels. One is a hardware in the loop, which means I'm able to actually build them, like we have different models, let's say BWR or molten salt or different models, where I'm able to bring that model into my simulation and it simulate in a real microgrid to simulate a real how the transition, the transient, the load following can act. So that's the low level, very precise, hourly basis simulator. I do have another simulator, which is a long-term nuclear renewable simulator. I call it NRHES, which is Nuclear Renewable Hybrid Energy System Simulator. Now, that simulator is very interesting because I had case studies. I had one case study for Indonesia, another case study for South Africa, and another case study we are trying now to build for Canada. We are analyzing, number one, what type of SMR could be suitable. Number two, what is the size of SMR that would be suitable? Number three, we can have a mix of those within solar, wind, and coal, and some other energy storage. And we calculate what is the energy capacity with load profile. So I'm able to say, if that is the load profile expansion from 2020 to 2060, based on that load profile and based on the price and the inflation and discount and lifetime of nuclear reactor and the lifetime of solar and lifetime of wind, we have those parameters in my simulator. I'm able to say what is the best mix of SMRs, whether it's SMR or a real reactor could be suitable, considering the lifetime of the reactor, the cost, capital cost, operation cost, all those fuel costs and all those. So we are actually, in our simulator now, we are able to do that. And I developed a very nice mix for Indonesia. And I tell them, I know your load profile. I'm able to tell you what is the best mix between 2 or 3 different reactors. And based on what is the best mix with the nuclear and renewable, like solar, wind. And I applied the same for South Africa. So that allows us, of course, in Canada, because we are still working on it, and also because there are some factors are keep changing. One of them is, of course, the policy. There are certain, like from OPG perspective, we would like to introduce SMR, and we start putting the map where are the SMR could be installed, and then we have the waste treatment. So I have a project for nuclear waste, SMR waste treatment with mobile units, etc. So I'm still collecting those pieces so that I can get some accurate numbers to be able to get the map. So I'm working towards that, and I'm getting the bits and pieces for now to reach that stage.
Interesting. That's it's really cool that you're accounting for factors like inflation as well, right?
Inflation.
That's important.
Yes,
that's important.
Absolutely. Because it happens in each country differently. And even, like, I remember I was talking to one researcher in our Smart Grid event last week. She's from Thailand. And she was telling that we would like to recommend inflation of the tax to be reached 300%. And I told her, we're already suffering from tax here, so you'd like to increase the tax further. So these type of things, like factors, like what is the tax impact on tax, like your carbon tax or tax on energy, energy cost, net present cost. So we are analyzing those, and I'm now collecting those bits and pieces to be able to put it in properly in the model to actually quantify the proper energy mix.
Phenomenal. I think this is a really important model for both Canada and for developing nations across the world.
And
right?
for SMR technology developers and investors.
Oh, wow.
Because the investment point of view, they would like to say, how much money do I need to invest in solar or wind or storage, and how much money do I need to invest in SMR? And if I am investing, how much ROI?
Yeah.
And we need to show them that you are able to get some sensible ROI. And one of the applications we linked with transportation electrification. One of the projects we said, if we have all Ontario vehicles or trucks or buses to become electric, how much energy do you need? If you charge on the same time, the grid is down.
Oh, yeah.
Trucks and buses, that's huge. So we made a number of models, and we even simulated as charging station, as a fast charging station for trucks and bus and boats and so on. We simulated that with nuclear renewable to say how the impact of SMR, how this look like with the grid and SMR and the renewable, and how is the load profile coming in. And we discussed even things like resiliency. I just had one master's student and one MNG student. We just developed a very nice report about the resiliency. What does it mean, resiliency, in terms of nuclear renewable portion and in terms of fast charging station portion? So we need to study resiliency here. It's not only safety, but also resiliency.
Absolutely, especially when gas prices are increasing to this rate.
Absolutely.
More people, I'm seeing a lot more Teslas, I'm seeing more electric cars on the grid.
Now it is a time to really find more resilient solution that is affordable and less cost and can deal with power outage and gas outage and gas price, like many factors here.
Absolutely. Yeah. According to your trends, I'm sure you may have played around with the simulator to see, according to the trends, what are you seeing in the imminent future? Are you seeing electricity prices in Canada rise significantly, or what's the trend that you observe?
That is an important question, because like in some countries, we found that from analysis point of view, some countries, they cannot, the SMR is not suitable to them for a reason that they need a large scale, for example. And we found that large scale really the main solution for the nature of the country. For some places, it is very, especially when in Canada we are very much wide, north, west, east, and very much wide areas. The grid infrastructure expansion is very costly. So definitely SMR is very useful, where we reduce and balance the cost of infrastructures to reduce it to become more focused and more local grids in different regions. That is more practical. So that's why SMR is very useful in Canada. In terms of the price, of course, I see the gas price is continue increasing. The greenhouse gas emissions and the requirements to reduce greenhouse and the carbon tax is continue increasing. So definitely the need for SMR-based grids and the power generation and supply will be the favorable option in the near future.
Interesting. Okay, that's really interesting to know. Well, sir, it was great chatting with you. We learned so much from this discussion, and I think your unique blend of nuclear, electrical, mechatronics, right? It's exactly what the industry needs, right? So I really appreciate your time, and I'm sure the audience does as well. Is there a last message that you'd like to leave with the audience?
I guess the first is we would like to collaborate more. Collaboration is very important. It's not the nuclear only can do the job. It's not renewables only can do the job. We need to collaborate. We need technology providers. We need end user, because end user, you are also having energy conservation strategies that can be implemented in the end user level. It can also help our new generation to think about new technologies and entrepreneurship and solutions that can fit into the integrated picture. And this is a special message to our grad students and graduates who would like to take some new ideas and lead them to the market. There are many, many points where it requires really Canadian technologies and the Canadian market where it can fit into the integrated picture. So I encourage really our students to start playing role, active role, and don't wait for just employment, but rather build something small that can fit into the picture. We have a lot of demands in technology controllers, smart transactive energy, interfaces, even policy analysis, even training for end users. So I think the best is the main message really for our graduates to work, to be active and play role in the transition. We call it energy transition. So the transition means we are moving from as is to be, but somebody have to do the transition, and we cannot wait for like utility companies or SMR technology provider. We have to play a role. Find your role and do it. That's absolutely, and don't be sort of like, try to be more positive and more active to help in that transition, because it will help all of us as a community and as Canadian and as future generation families and friends and kids.
Phenomenal. I think that's a great message to end off with. Be less complacent. Chase. Figure out your role in the industry. So thank you so much, sir.
Thank you. Nice to
Appreciate
meet you.
your time.
Thank you very much.
Thank you so much.